Will, please take it away.
Oh dear. All right.
One of these buttons at the bottom, right?
Yeah. But it is not
Yeah, it's on the screen.
Maybe you can disconnect, try to enable the...
All right, well.
It worked fine last time, of course.
Thanks, guys.
Actually, we did check it.
Yeah, we did. We did.
Checked it.
I intentionally didn't use my Linux laptop to avoid the situation. I knew it inevitably would happen, but it seems the curse
It has
stuck
to
with me.
happen once every session,
Yeah,
no matter what. So I think we're well within the boundaries anyways. Okay, let's try to connect again and see, hopefully we'll be lucky. Yes. I think you just have to kill that computer. Almost there.
Oh. Dear God. Unbelievable.
Yes.
All right, well, that wasn't supposed to be the challenging part. All right, so, hi guys, I'm Will Dietz. I'm here to talk to you about software multiplexing and how you can use it, how we used it, to both share your program libraries and statically link them too. So as a big picture, motivation. Most kind of the programs today are built around this notion of shared libraries, which is, there's a lot of good reasons for that we'll come into shortly, but as the motivation goes, that's kind of a limiting situation because there are these opaque objects that your compiler can't see into, and kind of or doesn't really understand the overall deployment context into which they're made available, right? So you kind of build them and ship it, and then something dynamically pulls them together. And so, as I mentioned here, the consequences are of this, as we'll show, is that this kind of limits your optimization opportunities available. It can cause redundancies, or rather, makes you tolerate the existing redundancies in your system, so you can't do anything about them. And at least in today's world, when you say shared libraries, you mean, at least everyone seems to mean, this dynamically linked and dynamically loaded. Historically, they were not always that way, but that seems to be married to the idea today. To kind of refine this point a little further, on this notion of shared and their kind of companion static, there's a lot of trade-offs between the two that you're kind of forced to make as a set of one. You must say have all of one or all of the other, such as shared, and this is kind of the big one, right? It's in the name, shared, sharing. The less you can share them across the applications, as opposed to static, you're copying them with you, which if everyone includes what they need, you might end up with these duplicates. Shared, of course, also, and this is kind of related to the dynamic aspect, is used for plugins, loadable extensions. Honestly, it's, like I said, it's the most popular one, so they're used for everything. Static can pose certain challenges to being updated, especially in the way package management and distribution and deployment is handled today. DLL hell is a term to describe the special situation that involves shared libraries. It's also why you can't just take your application and trivially copy it and share it with your friend and have him run it, right? You end up, it's not just the application, an application becomes the environment in which it's reliant on the environment it's in. And details about that is what causes DLL hell. And all these other points as well between static and shared, which I will be happy to discuss later because of. But the main big thing about shared is sharing, as I said, and that's what largely leads to them being dominant in today's domain. So shared, as I said, reduces one aspect of this duplication between or possible duplication in your kind of deployment scenarios. But there's other kinds of duplication that aren't really addressed, right? So if you have multiple versions of a library, the shared library, it won't, kind of model doesn't capture that, at least not in any normal way, right? But of course that happens all the time as you push new versions and whatnot. Similarly, there's multiple versions of an application. And even more beyond the granularity of these libraries, right, however they were formed and shaped and packaged, is that you could, of course, duplications of functions in the code that your program consists of. And all of this is kind of made opaque to the conventional model. And shared libraries address the first one, but not the others. The software multiplexing and kind of the grander ALLVM approach that we're talking about is a frame that lets you address kind of all of them together. So all right. Here we have, as a kind of an example to be a little bit more concrete, an LLVM release. And there's built in multiple kind of configurations. And at the top we have the static, and in the total size of all the binaries, when built statically, is 600 megs. And the very far end, if you build it in all the little shared libraries, you get this 100 megs, which again is one of the main benefits. We like these sharing, right? But excuse me. But actually, that's the performance trade-offs between the two are such that they've introduced a kind of third hybrid solution where they form, they kind of combine all the shares into a single libLLVM in the middle, which they're able to do because they're compiler engineers and they spend time on it and that works. But it just kind of speaks to these two extremes aren't enough. But you can see there's a huge size difference. And yet, even so, when we do this multiplexing, our result is even smaller without making any of the compromises, as we'll show. So, for example, these bars are the performance of building LLVM with LLVM. We're an LLVM group, so it's a very common thing. And if you've built LLVM, you'll understand why it's a very important benchmark. It takes a while. So the execution time of doing this is very much impacted by the build configuration you're doing, right? So, and this, if you built it all statically, even though it's much bigger, it takes less time, right? If you have it fully shared, which actually I don't think they generally discourage for this reason, LLVM has so many pieces that if you build it into all its little libraries, it's kind of silly. LibreOffice is known for being the same way. And libLLVM is kind of like this compromise. And however, with multiplexing, where we end up producing a single static thing, we're able to get even faster. So all of that said, I'm hoping just to get you guys excited about what's possible. The other aspect of this, the other dimension, right, of besides performance, is the memory footprint, memory and disk. And here we're focusing on memory, but the cool thing with shared, and kind of the thing that comes to mind, right, is that you can have only one copy of the code page in memory, just no matter how many programs are using it. And so in this graph, we have on the bottom the number of applications that are concurrently running. And as you can see, the blue and the red are both builds using shared libraries, and they grow. They get a little bigger because when you have a different application running, it does need some memory. These are distinct programs, not copies of the same. But if you look at the static line, it grows roughly linearly because everything needs a complete new copy. And so what this, even though we got it faster, you end up using a lot more, you need more space to do it. And this is kind of an unfortunate trade-off to be forced to make as we build things. And with multiplexing, however, we're able to, I'm very excited about those results, to use much less memory while even getting the performance benefits. And if you know a good way for us to measure the Clang memory usage for this, I'd like to include that as well. But it's kind of hard to remember as opposed to running these desktop applications. So yeah, it kind of gives you the best of both worlds in these measures for multiplexing. And for that reason, you guys should be excited. I am. So all right, how does it work? And this is kind of where we'll be talking. I've said a lot about multiplexing. You guys have been very patient with me not saying what the heck really it is. It's kind of simple. That's its strength, I believe. It's this process of taking these n applications and all their libraries, and combining them into a single statically linked self-contained program. And I mentioned it as multicall. It is a couple terms for it, but basically, the single program knows which of the programs that have been combined into it to run based on how you invoke it. It's a common thing. You see it in a lot of embedded systems or other manual uses. Actually, Clang itself uses it in the driver in a very limited sense. But what's particularly cool is that we're able to do this at, in my world, scale, which is to say, we can build thousands of programs this way. Most of the software I run on my laptop is built this way. There are limitations, but frankly, it's surprisingly effective in the sense that I set out to find its limitations and discovered that I got a lot further than I expected. So if you're skeptical, I understand, but it actually worked out pretty well. And as I mentioned here, basically no changes are really needed to your make files. So the first process of this is creation of a thing we call an allexe. It's part of our ALLVM system, a system in which everything is built with LLVM bitcode, to tackle these kinds of problems. And basically what you do is you build your program, and you build all the components into bitcode. And in today's world, that's not so hard. LLVM is kind of the thin waist, right, between all the programs that exist and all the formats that it could go to. There's a compiler somewhere that will push it through LLVM at some point. So if we take these and run it through, well, our tool is called BC2LLVM. But the important thing in these allexe creation is that you end up with basically what is the code in your program? And generally speaking, that's not such a hard question to answer, and it kind of shouldn't be. But if in a domain where that's the hard question to answer, this would be kind of a challenge. It hasn't been a challenge for us yet, but I just thought I'd mention it. Like I said, lots of Linux applications this works well for. And so with allexes themselves are actually, we use them. You can run them and JIT them and do all kinds of cool LLVM-y things with them. The other part of this software multiplexing is this automatic multicall. It's a relatively simple compiler transform that it just generates the dispatch on name to the program logic that you would expect. There's a couple more details to handle involving static constructors and destructors for the shared libraries, but that actually turns out to be pretty simple to handle as well. It's in the paper, and actually, since I don't think I mentioned this elsewhere, I thought the whole tool is available online, so you can look at it too if you're curious. And then finally, this library deduplication, which is basically just instead of copying the libraries, we just, when you merge them, just have one copy. It's as simple as it sounds. I apologize, we're running a little short on time. But one cool thing that's not in the paper that I wanted to share with you, just because it's exciting, is this. You guys are familiar with LEMP? It's a popular web stack. For example, with multiplexing, we're able to take Nginx, MariaDB, and PHP, and combine them into just one program that represents all the functionality of all of them. And you can actually even use that in a deployment. It does take a little bit of you have to tell it to run. Never mind, it works well. And the result is significantly smaller. And of course, it's because it's static and everything else. And it only contains the code it needs. It's actually very ideal for example, like a Docker or other kind of DevOps-y kind of deployment, right? Yeah. And further going on to kind of our results, this is a whole bunch of applications that have a single program in their package build, and the bar is the size of the overall deployment, right? The runtime closure of the code you need, and we're normalizing it to the dynamically linked variants as normally done. And as you can see, we get a significant savings across all the all these programs, and there's much more, but then the bar's gotten readable, so we just have these. And beyond that, we have, when you start looking at an important kind of case for multiplexing that, again, this is a dimension that you don't really think normally or isn't solved normally by conventional sharing, is that when you have a package, it's very common that you produce multiple programs, right? Like utilities and such, and you either don't have a library for it, or you don't really want to have like exposed to the user this like library, right? But of course, your code it's redundant in a lot of ways. And so here we're showing a bunch of programs, a bunch of packages that have between 2 and some hundred binaries in them. Some of them are actually collections of packages. The one at the very end, for example, is a collection of all the file system tools that I've ever heard of, like for all the like ES tools and the FATMO tools and all the formats. Again, you can see that this you get a similar, reduction savings. And honestly, one of the main things I want to show these graphs is just that it actually even like built and worked and runs for all of it, because I know I was pretty excited that that was even possible. And another kind of a cool result is that we took, using multiplexing, where you can combine across versions. This is the other axis of duplication that I mentioned earlier. And you can combine, here we combined 40 different, at the time, all of the versions that have been publicly released of memcached into a single binary. This is normal, and I think the cross point was, with multiplexing, we got 15 versions to fit into what normally is one version. But certainly compared to the dynamic of all 40. And this kind of just shows how it scales as you so at 2, we're combined 2 versions versus dynamic of 2 versions, and so on. I don't know, it was just really cool. And kind of in contrast to, perhaps with this, I mentioned earlier this library deduplication technique, and it turns out that's kind of important, although conceptually it shouldn't really be important. It just kind of turned out that LLVM was less effective at removing obviously redundant code than I expected. So the library duplication technique that is mostly just about pointing it out to LLVM. And here and this is also in the paper, we just show that if you don't do that explicitly, you end up with these glaringly redundant code, and it ends up actually being bigger. So it's kind of important, at least for now, to do that. So limitations. I'd like to tell you this is, does everything and it's wonderful, and it is wonderful, but there are situations that it doesn't make sense for, and most of them have to do with you can't predetermine what your program's code is, then this doesn't make any sense and it won't work. And in particular, if you're constantly adding or removing executables to your system, this is a somewhat expensive process to push through the compiler, at least in the current form. So updating that takes a little bit of time. Updating libraries, if you want to just replace the library in the middle of a big multiplexed set, that's something we're working on, but at the moment is going to be kind of expensive. And so, and it's just, as much as anything else, it was a self-imposed limitation to ensure that programs weren't sneaking in code that we didn't account for, and that's that. This dynamically loaded through DLOpen or introspection through DLSim, if that's not allowed as well. And yeah, so, all right, in summary, software multiplexing is a technique for sharing library code without dynamic linking. It often produces much smaller and, depending on who you're comparing against, either slightly or much faster programs. It's largely fully automatic, thousands of packages, and as I mentioned before, one of the most compelling use cases are these packages that produce multiple binaries, but there's a bunch of other situations. So thank you all for your time, and I'll now take questions.
Hi. So you said, you sort of suggested that the process of linking this all together was sort of expensive, and so if you were constantly updating your binaries, then
Yeah.
you probably wouldn't want to do that. Can you just give me a sense of what expensive means? Are we talking about, oh, you'd have to, give it an hour, or oh, you'd have to give it a week?
Well, it depends how many you push together.
Of course.
Right? If you're pushing together gigabytes and gigabytes, you probably won't at the moment. But we're using a somewhat dated version of LLVM, and as far as I know, there's no real limitation for that necessary. It's just that the
Can you give a sense for like the memcached all-40? Like what kind of amount of time are we talking about? Just like an order of magnitude.
I think that one didn't take too long. I think it was a minute. Short enough that I didn't really care. I can tell you that the larger the QT experiments where I'm combining hundreds of megs of stuff, that took long enough that I generally tried to not do it on my laptop. But I mean,
But hours, not days.
absolutely, that nothing would took days. And I can any of those numbers, if you're actually curious at all, I'd be very happy. I have all of them. They're all logged. I'd like to make them available. It's just I don't know them immediately, unfortunately. But how about 1 hour? I'm not sure. I'd rather be wrong in that direction than over-promising.
Hi, very cool work. I wanted to wonder about package management. When I'm installing this stuff and I'm keeping the sort of semi-shared libraries around, how many representations do I need to keep around?
It's a great question. So part of what this is a kind of an experiment in how things could be, right? But at the moment, if you have this as bitcode and you want to be able to regenerate things using the bitcode, you kind of need multiple form versions. And when you add all that up, that would be more expensive. But the kind of at least all these numbers in their deployments, there's no reason that that you couldn't take the and this is kind of, again, it fits very much in the cloud push, generate an image push model where you would generate it. But if you were doing it on your desktop, at least in the current form, because you can't execute it in the same form that you represented it, you need to either keep it around or just refetch it when it was time to build. So your question was technically how many, so I guess at least 2, but I mean, and that's handled through a garbage collection. This is all built on, well, I've built it all on top of the Nix functional package manager. And so, okay, so I don't know, I just clean it up when it gets too big, but I don't know, I do most of my research on my laptop and it's not anything impressive, so it doesn't seem to be too problematic.
Hi, thank you for your talk. You mentioned there's no new security vulnerabilities, so in Unix, usually the permission bits in the file system enforce security. How do you handle security of one executable versus another?
I'm not sure I understand your question.
Okay, so let me give you an example. Let's say you're multiplexing cat and fdisk. How can you make sure that your user can run cat, but he cannot run fdisk without being root?
At the moment, I don't have a great answer for that. In some ways, you can kind of, this is actually in some ways it got derived. You can kind of think of the multiplexed as a cached evaluation of all of your system and its code. And so if you view it that way, then I think that you can make it work with the permission. But it get messy, and I think you can make that work, but honestly, I haven't worried too much about it. But you're right. So I think for the model will be mostly that you have some trusted user creating these things, and then everyone can run it.
That's fine. Thanks.
We're a little bit past the allocated time, so if you have any more questions, please take them offline. Thank you very much for sticking around. Let's thank the speaker again.